And last time we got into type 1 ionic compounds. Remember that if it's ionic, it is a metal and nonmetal together. No sharing of electrons, cation, anion interaction. And remember that whenever you got a metal involved in naming, that is the most important thing. That really determines sort of how you go about naming it. And a type 1 metal basically has a fixed positive charge. And that's pretty much your group 1, 2, 3 on the periodic table, which is basically aluminum. Zinc, cadmium, or silver, which are 3 transition metals that actually still have a fixed positive charge, so they fall under this. And if you do identify it as a type 1, pretty much all you need to do is go whole name of the metal, and the non-metal will get the IDE treatment at the end, where we drop the last part of the non-metal name. Now, if it's a type 2 ionic compound, once again, you will have a metal and a non-metal. And the metal, again, is the most important thing. Pretty much, as I mentioned, any type of naming, you have a metal involved. Pretty much that's what you should look at in terms of how you should determine how you should name it. These guys have a variable positive charge. And that basically is going to be your transition metals are just to the right. Again, as we talked about, sort of underneath that staircase on the periodic table in this sort of area where you got lead, tin, those type of guys, which are not necessarily transition metals, but they also have variable charges. The deal on that is because it can have variable charges, we have to add one thing to our naming here, which is we go with the whole name, again, of the metal. We have to insert a Roman numeral in there. And the Roman numeral is for the positive charge on the metal. And again, it is not for how many you have, which is a very common mistake. It is if you just took one of those kind of positively charged ions out, what the positive charge is on that one ion. And the last guy there still is named the same way. We're going to add the IDE to the end of the name. The good news is, as we talked about, if it is a type 2 sort of metal, you will always know the charge of whatever it's attached to. So all you have to do is to sort of work your way backwards, remembering that obviously the overall charge needs to equal 0. So whatever it's attached to will basically determine, thank you, the charge that it has on the positive guy. Then we got into type 3, which are covalent or molecular compounds. They got 2 nonmetals together. Remember that these are pretty much straightforward because they are covalently bonded. They're sharing electrons. There's no ions. So if there's no ions, you don't have to worry about figuring out charges or anything like that. And this is the place where, again, we do use prefixes. Again, like mono is 1, di is 2. I guess that way. Tri is 3, tetra is 4, and so forth. Now, there's a couple of rules that we talked about. We do not use mono on the first name. But the second is okay. And the other major thing that sort of happens with this is the prefix vowel at the end and the vowel on the element name sometimes backs up to each other. So sometimes we get an A and an O, or an O and an O that sort of back up to each other, one from the prefix and one from the letter of the element. So typically speaking, when that happens, we do get rid of the vowel on the prefix. We leave, obviously, the second vowel, which is the same there as well. So again, like through our example we talked about there, this is carbon, no mono on the first name, mono on the second name, drop one of the O's there from the prefix, and this becomes carbon monoxide instead of carbon monoxide, again, with those 2 O's. But basically, we prefix if necessary or needed, and then we use the whole name of the first element, and then we prefix the second guy, and that guy is like pretty much normal. It will get the IDE treatment at the end of it. Any questions on any of those naming? Remember, again, prefixes only here in type 3. You should not be using prefixes typically if you have a metal involved, because it probably is incorrect. Any questions on that there? Okay. All right, so there's our review there. Again, type 1, ionic compounds, fixed positive charge, no Roman numeral. Type 2, variable metal charge, needs a Roman numeral. And type 3, no Roman numerals, only prefixes, molecular compounds. So let's talk a little bit about compounds that contain polyatomic ions. Polyatomic ions are actually groups of non-metals together that actually have charges. So this is an example here. This is NH4NO3. We could actually break this guy up right about there. And we actually have two polyatomic ions in this case. This is NH4 plus. That one nitrogen, those four hydrogens all stay together as a whole unit. It moves around as a whole unit. It doesn't break apart because those are nonmetals and they're actually sharing electrons, and it has an overall charge of +1. Same thing here. This is NO3 minus. Also, that one nitrogen and three oxygens stay together. They never break apart because they're sharing electrons and they move around as a whole unit. Has an overall charge of -1. That is why we only need one of each of those when we put them together in a formula, because basically equals 0 charge like normal. We've actually drew these guys when we did Lewis structures. This is NH4 plus, looks like this. Again, sharing of electrons here. And this is our friend nitrate, which looks like this. So again, this is basically the two things that are coming together here, and they are sharing electrons, but do still have a charge. So they're kind of unusual species in that sense that they share electrons, but basically because of who they're sharing electrons with and how many, they actually gain sort of an overall charge and are ions. So each of these things have a special name. This is the ammonium ion, not to be confused with ammonia that does not have a charge and has one less hydrogen, NH3. This is the nitrate ion. Now, the good news about polyatomic ions, if there is good news, is it doesn't matter how many of them you have, you just use the name of it. Whatever the name is of that polyatomic ion, when you go to name it, you would just use the name. So obviously here, when we put this guy together, we would use both names, and that would be ammonium nitrate. Now, a vast majority of the time, you will not have two polyatomic ions together, and that is because there is probably only about 3 positive polyatomic ions. Most of the polyatomic ions are actually negative. And because of that, what happens probably, I would say 99.9% of the time, is you will find yourself with our friend the metal and a polyatomic ion coming together. So a lot of times what happens is you'll actually have a metal with the polyatomic ion because, again, most of them are negative. And what that means is, as we talked about previously, the metal is the most important thing. So basically, you're just going to decide, is it a type 1 metal or a type 2 metal, basically. The polyatomic ion doesn't matter because you just use the whole name. So it doesn't matter, if you have 2, 3 of them, you're just going to use the whole name. So basically, most of the time you will have probably a metal that's hooked up with a polyatomic ion, and you basically got to decide, do I need to include Roman numerals or no Roman numerals because of the metal? And again, you just use the whole name of the polyatomic ion. Questions on that there? So there is a list here of some polyatomic ions, which you should know. They want you to know. And as you can see, most of these polyatomic ions are negative, pretty much. NH4 plus is a positive one. H3O plus, which is hydronium ion, is also positive, but there's very few positive sort of polyatomic ions. So you do need to know these, and what's a good way to know them? I would say Most of the time, there are some patterns that you could think of, and it'll help you sort of understand these. So, for example, if we take this guy here, which is NO2 minus, that is nitrite, ITE. NO3 minus, that is nitrate, ATE. The only difference between those two is the number of oxygens. They both have a -1 charge. They both have a nitrogen. The difference is the number of oxygens. If we look at SO3 2 minus, that is sulfite, ITE. SO4 2 minus is sulfate, ATE. Again, the only difference between those two things is the number of oxygens. They both have a -2 charge. They both have one sulfur. So most of the times in a group of two, the one with the least number of oxygens ends in ite. The one with the most number of oxygens ends in ate. So that's a really good way to maybe learn it and group them by twos. You could also, if you wanted to, learn all of the eights, if you will. And all you have to do is take off an oxygen if you needed the ites. So you just take off the oxygen, everything else stays the same. Or you could learn all the ites and know that all you have to do is add an oxygen and you'll have all the eights. So for example, if I remember that SO3 2 minus is sulfite, but I need sulfate, all I have to do is add one oxygen, everything else stays the same, and I will have sulfate. So it's a good way to kind of remember them in that sense as well. Now, there's also in polyatomic ions groupings of 4 things that are related to each other. That's probably one of the most common ones there. That is ClO minus, ClO2 minus, ClO3 minus, and ClO4 minus. So we basically have this. They all have a -1 charge. Again, the only difference between all these guys is the number of oxygens. So we actually kind of break it apart the same way. Obviously, to my right here, those are the guys with the least number of oxygens, which means they should end in ITE. And this would be chlorite. And this guy should be chlorite because they have the least number of oxygens. But you obviously cannot have the same name for 2 different things. So when you have a group of 4 that are related to each other, the one with the least number of oxygens in the group of 4 will also start with hypo. So that is hypochlorite. The guy next to it is chlorite. Now, if we go to the left of the line, those are the guys with the most oxygen in that group of 4, which means they all should end in ate, right? And that would be like chlorate. This would also be chlorate. Once again, you cannot have 2 names for 2 different things. So in a group of 4 that has the most oxygens, we put per in front of it, and that is known as perchlorate. So that is perchlorate, chlorate, chlorite, and hypochlorite. Again, the only difference between this group of 4 is the number of oxygens. So again, if you just remember one and know pers for the most of 4, and hypos for less, you could just adjust oxygens and figure out the name. So if you remember chlorite and know you need chlorate, that's 1 more oxygen. If you need perchlorate, that's 2 more oxygens because that's a group of 4, so we need 1 more to go on it. That Cl that's in here is a group 7, right, which is a halogen. You could actually swap out this for any halogen. So if I had BrO3 minus instead of chlorate, what do you think the name would be? Br is bromine, so that would be bromate, yeah? And if I had BrO2 minus, that would be bromite. So you could actually swap out any of those guys. If I threw an I on that, that is iodate, right? So they all kind of work the same way if you swap out any of those halogens along the way. Now, other things that you'll see on here is what we see right about here. This is carbonate, CO3 2 minus, and if you put a H plus on it, it becomes HCO3 minus. The charge changes because you put a +1 and a -2, leaves you a -1 overall. We put a hydrogen on it, so surprisingly not, it is called hydrogen carbonate. That is also sometimes called, very commonly still to today, bicarbonate. And bicarbonate is used instead of hydrogen carbonate. It is used a lot still by people today. We also see that with sulfate, hydrogen on top of sulfate here. That then also is known as bisulfate. So bisulfate and bicarbonate are two names that are still used a lot today. Now, we also have some things that do not end in ATE. There are some polyatomic ions that do end in IDE, like that is peroxide. There is hydroxide and cyanide. These guys end in IDE, but a vast majority of your polyatomic ions end in ATE or ITE. Now, if you look at phosphate, which we have right here, that is PO43 minus, right? That is phosphate. If I wanted phosphite, what should it be? ITE at the end, what should it be? PO, more oxygens or less? PO3, just one less, right? 3 minus would be phosphite. So that's how you can sort of adjust. If you at least know one of the names, you could go just up or down. It's just an oxygen that changes, like so. Um, if I had my sulfate, my sulfite. If I wanted, for example, hyposulfite, what would it be? That's sulfite. So what should hyposulfite be? More oxygens or less? Less, right? Hypo is like a group of 4. So I just take one oxygen off. That's it, right? SO2, 2 minus would be hyposulfite. So again, if you learn them and learn how to kind of just adjust them up or down with oxygens, it's a lot easier than trying to just like remember everything individually. Or if it works for you to remember everything individually, you could do it that way. But sometimes it's good just to know how to adjust it. This is the only place, for example, that I was talking about earlier where you could have a metal and a prefix together. And the only reason you would have a prefix is something like this guy right here. The name of this guy is dichromate, which is a prefix, but you didn't put it on there. It is actually part of the polyatomic ion's name. So that is the only place where you could have a metal and an actual prefix, but the prefix is not really put on by you. It's actually the name of the polyatomic ion has the prefix in it. Other than that, again, you should not have any type of prefix. Any questions on that there? All right, so here's another list that again has pretty much the same ones on there. But let's take a look at some of these here. Why don't you give the name for the following? Let's do FeNO3 2. Let's do NaClO3. Let's do NiCrO4 2. And then why don't you write the formulas for this? Ammonium sulfide, copper 1, actually copper 2, copper 2 hydroxide. And let's do aluminum thiosulfate. All right. So names there on the left and formulas on the right here. Okay, so let's take a look, see how you're doing. Again, here, we want to kind of identify always sort of what we're dealing with. So we have iron, which is a metal, and we have NO3, which is NO3 minus right there, which is nitrate. And remember here that every time a metal is involved, that's really what we should determine. So the first thing we want to think about is, do we need Roman numerals with this guy? The answer is yes, because he's a transition metal. He's dead center in the transition metal region. That means he has a variable charge. So we do need to figure out what the charge is. The same rules apply as what we did earlier. We will definitely know the charge on nitrate, which we can see is NO3 minus. And there are, how many of them? There are two of them. And that means that overall we have a -1, -2 charge. So in this case, our iron is going to be +2 in this case. That will give us a name of iron, Roman numeral 2 for the charge on the iron. And again, even though there are two of the polyatomic ions, we just use the name, and that would be iron, Roman numeral 2 nitrate. Questions on that? The other thing that we see in the formula is there are parentheses around the polyatomic ion. And whenever you have more than one polyatomic ion and you're writing the formula for it, you do need to put parentheses around it and the number on the bottom. Otherwise, if you do not do that and you just write it like this is no good because it implies that you have 32 oxygens, which is not really what you mean. So always you need to put parentheses around any polyatomic ion in a formula that you have more than one of. If you just have one, you don't need the parentheses, but definitely if you have more than one, you do need the parentheses. Any questions on that one there? Same thing here. We're going to look at this. This is sodium, which is a metal. That is our polyatomic ion, ClO3 minus, which is chlorate right about there. And again, here is going to be the metal that's going to help us determine. And with sodium, it's group 1, which means it has a fixed positive charge and is a type 1, which means I do not need to figure out the charge. I just need to use the whole name, which is sodium. And here I will use the whole name of the polyatomic ion, which is chlorate. Any questions on that one there? Lastly, down here we have nickel, which is a metal, and we have CrO4, which is CrO4 minus, which is right there. That is chromate. And in this case, nickel is again a transition metal, which tells you it's a type 2 compound, and you do need to figure out the charge here. So we'll just take our normal approach. We have one nickel. The polyatomic ion is CrO4 minus, and there are two of them. Again, counting up the negative charges, that is a -4 overall from the two chromates. And that means to balance it out to 0, we're going to need a +4 on our nickel. And now we could give our name, which would be nickel, again, Roman numeral 4 for the charge on the nickel. And just the whole name of the polyatomic ion. Doesn't matter if you have more than one in this case. Any questions on any of the names there? All right, now that we have formulas, we're going to do kind of a similar approach. We just want to put them together. So ammonium is actually a polyatomic ion, which is right there, and that is NH4 plus. So this guy is NH4 plus. Once again, that whole entire thing has a +1 charge. Sulfide is actually sulfur from the periodic table. So that is group 6, which has a -2 charge. That means in this case, when we put this together, we actually need one more of the positive guys to balance it out. And because that is two of the polyatomic ions, we need a parentheses and a 2 to say that we have two of them, and then just one of the S's there. Any questions on that one there? Looking at the next one, we see copper Roman numeral 2 hydroxide. So copper with a Roman numeral 2 means my copper has a +2 charge. Hydroxide is -1, which should be somewhere up here, right there. OH minus. So once again, we're going to put this together to equal 0. That's a -1 and a +2. That means we need one more of the -1s here to balance it out to 0. That would give me one copper. Again, we have two of the polyatomic ions, so I do need parentheses, and a 2 there on the bottom. Questions on that one there? And lastly, we have aluminum, which is group 3, so it has a +3 charge. Thiosulfate is right there, and that is S2O32 minus. That's a lot of letters, but pretty much it has only a -2 charge and a +3 charge. So we want to put that together basically to equal 6, right? That would be the common number. So to get aluminum to 6, I do need 2 of them. To get my thiosulfate to 6, I actually need 3 of them, right? -2, -4, and -6. So putting that together in a formula here, we have aluminum and 2. Again, we will need parentheses because we have more than one of the polyatomic ions. And we will need a 3 on the bottom there. Any questions on any of those guys there? So much like everything else at the school, they want you to know them. Yeah, so you have to learn the polyatomic ions. They will not be provided. So again, find whichever way works good for you, pattern-wise. But you do need to know, obviously, the formula and the charges so you can put them together correctly, and the names. Yes. Any questions on that there? All right. Here's another table in case you didn't like any of the other twos. All right. Last thing we're going to talk about, actually, here's our patterns we talked about already. So I think we'll scroll through this here. All right. So last thing we're going to talk about is naming acids. And an acid is a substance that has the ability to produce H plus ions in solution, hydrogen ions. They are sometimes referred to as protons. So if it's an acid, pretty much it has the ability to release an H plus into a solution and allow it to basically float around freely in there. Pretty much when we talk about acids, the cation for all acids is H plus. So the positive guy for all acids will be H plus. And basically, the rules for acids is this. It all depends on whether or not there is oxygen. So if there is oxygen in your acid, which is sometimes referred to as an oxyacid, you name the acid a certain way. If there is no oxygen involved, then you name it a different way. So really what you want to look at is there oxygen or not? So let's just talk about how to go about doing that. So if we have no oxygen involved, we basically will have an acid that starts with hydro, something ic acid. What is the missing part? The missing part is the negative ion that's attached to it. So if you have HCl, no oxygen. So this would be hydrochloric acid. Again, for the chlorine that's there. If you have HBr, again, no oxygen. This would be hydrobromic acid. We also, as you can see, for acids, put the aqueous symbol next to it because that implies that it is a solution, and those are basically what's going on in the solution part. That is different than if we had HCl that, say, was a gas. That would be called hydrogen chloride. So with the aqueous, it kind of tells you it's going to be an acid in this case, and you typically do put that next to the formulas of anything that's an acid. So basically no oxygens, starts with hydro, ends with ic. Middle part is the negative guy. By the way, the cation here is H plus. The anion is Br minus. Same thing here, H plus and B and Cl minus for our anion in that acid. Now, if your acid does have oxygen, if it does have oxygen, It will most likely contain a polyatomic ion. And as we just saw, they typically will end in ate or ite is typically where the polyatomic ions end. So if it is yes to oxygen and your polyatomic ion ends in ate, your acid is something ic acid. So for example, HNO3. NO3 is nitrate, ATE. This is nitric acid. H2SO4. SO4 is sulfate. This will become sulfuric acid. There are two hydrogens here because we needed to balance out the -2 charge from sulfate. Yeah. So that's why, again, we have two hydrogens in that case. Question on that one there. Now, if your polyatomic ion does contain oxygen and your polyatomic ion ends in ite, your acid name will be something OUS acid. So HNO2. NO2 is NO2 minus, which is nitrite, ITE. This will become nitrous acid. H2SO3. SO3 is SO3 2 minus, which is sulfite. This will become sulfurous acid. So what you can remember it is you ate too much, you feel icky. Yes, that's how the acid should end, right? ATEIC. Yeah. So there is absolutely, as you can hopefully see here, when you have oxygen involved, no hydro. So hydro is only for ones with no oxygen. People like to throw hydro on everything. So no hydro on anything that has oxygen, only those that do not have oxygen. Question on that there. All right. All right, so let's see here. All right, so this is what we just talked about. Hydro, if we do have no oxygens, and obviously ic or us if we do have oxygen, no hydro in the front of it. So here's some examples. HF, which is hydrofluoric acid, HCl, hydrochloric, hydrobromic, hydroiodic, hydrosulfuric acid, and hydrocyanic acid. All no oxygens, all have hydro and an ic. Yeah, as you go through it. Here again, nitrate, nitric, nitrite, nitrous, not sulfate, sulfuric, sulfite, sulfurous, phosphate, phosphoric here. So again, by the way, that is acetate, acetic acid. Yeah. By the way, acetate is sometimes written, speaking of polyatomic ions, like that. Sometimes it is written like this. So acetate is sometimes written in multiple ways, but it's basically the same thing. All right, so obviously here, why don't you give the names for those guys? Why don't you also write the formula for perchloric acid? Why don't you do carbonic acid? Why don't you do chlorous acid? All right, and why don't we just add one here? Let's do this one. All right, names here on the left, formulas on the right there. Okay, let's take a look. So we'll start first one here, HF. It's an acid. I don't see oxygen, so I know it's going to start with hydro something ic acid. And again, the something is the anion here, which is F minus. Remember that H plus is the cation for all acids. And that'll give me something like hydrofluoric acid in this case. Looking at the next one, we do see oxygen, and that means there's a polyatomic ion hiding in there, which is NO3 minus. That is nitrate ATE. That means my acid is something ic acid, and again, that's going to be nitric acid there. So that will be nitric acid in that case. Same thing here. We got PO3, which is a polyatomic ion. That is PO3 3 minus. That is not phosphate because it has one less oxygen, so it's actually phosphite, ITE. And that means that this would be phosphorus acid. Any questions on those there? Again, H plus being the cation for each of those. Now, if you have the name and you want to work your way backwards, a couple things you can get from the name. Clearly, I do not see hydro in the first name, which means that it does have oxygen, right? And when I know it has oxygen, I know that it should have a polyatomic ion. And I see that this acid ends in ic, which means the polyatomic ion should end in 8. And if you're not sure what the polyatomic ion is, you could cross out the ic and just write 8, and that says perchlorate. So that is your polyatomic ion that you're looking for, perchlorate. And we know always that the acid is H plus. So now all we do is put it together, and we will have our proper acid in this case. Same thing on the next one. I do not see hydro, which tells me there's an oxygen in it and it's polyatomic ion. Once again, this ends in ic, which means my polyatomic ion ends in 8. And if I put 8 in there, it kind of looks like carbonate, right? And that would then tell me that is the polyatomic ion that I'm looking for, which is carbonate. Again, H plus here is our cation. We need to balance it out to 0. So we need 2 of those guys to do so. Gives us H2CO3. Question on that one there. Chlorous acid, again, no hydro, which means it does have oxygen. It also is a polyatomic ion. But this one ends in OUS, which means that the polyatomic ion ends in ite. So if I just cross it out and write ite, that says chlorite. And that would be the polyatomic ion I'm looking for, which should be that. And H plus should be my guy and gives me HCOO2. So if you have one of those acids that contain a polyatomic ion, you could kind of cross out the ic or the us at the end and put 8 or ite, and you'll pretty much have the name of the polyatomic ion that you should be using, and then you just need to balance it out with H plus. Any questions on that? Questions on naming? Yes, you're now naming professionals. Congratulations. All right. That is it there. All right, we're going to go off to chapter 6 now, I think, here. Okay, we're off to chapter 6, which is a pretty quick chapter. It's all about equations and reactions and balancing equations. Obviously, a chemical reaction is a chemical change, which means whatever we start with and whatever we end with are fundamentally different things. We have created something new. And evidence of chemical reactions occurring are a few different things that you could see, or maybe not see. Come back here. Color change is evidence of a chemical reaction, or could be. Obviously, if we started with something that's colorless and you make something that has some color, then it is. A solid being formed is definitely an evidence. That is some type of precipitate that's made. Bubbles being formed means that you've created a gas, so some type of gas has been generated. Also, something catches on fire or heat also is evidence of a chemical reaction. If you're holding a test tube, it gets really hot, that means you're giving off heat, something's happening. Or if it gets really cold, that means it's an endothermic reaction, it's sucking the energy out of your hand, and that's also evidence of a chemical reaction. Pretty much there's three reasons why a reaction takes place. One is the formation of a solid or a precipitate. The formation of water is another reason why a reaction takes place. And lastly, electrons being transferred. As we will talk about probably in the next chapter, you could pretty much boil down any type of chemical reaction that you see to one of those three things happening is basically why it's happening. Either you made a solid, you made water, or there's some electrons being transferred in those reactions. And that's really, for the most part, the three reasons why every reaction takes place. If none of those three things happen, you probably won't get a reaction. So nothing will actually occur. You'll get no reaction that occurs. Something you'll do a little later here today, maybe not exactly like that, but you'll do a little electrolysis of water. If you run electrical current over water, you will break it apart into hydrogen gas and oxygen gas. Those are all the bubbles that you see there, the hydrogen gas and oxygen gas coming off. Obviously here, some color changes. That's also what we'll be doing today, a little lead to iodide made there, that yellow solid. And obviously bubbles there, some type of gas, and obviously fire happening. So one way that we represent a chemical reaction is to use a chemical equation. And when we look at a chemical equation, we can write it in words or have it in words and put it into formulas. When we have something like hydrogen gas burns in air, which contains oxygen to form water, we get H2 plus O2 makes H2O. It's really important when you write chemical equations, we do need to make sure that they are balanced, as we'll talk about. But frankly, you should always make sure the first thing that you do is you have the right formulas. And if you do not have the right formulas, it's going to take an all-day project to balance it. It will not work. So very commonly people mess up by trying to balance and write the formulas at the same time. You should always keep this in mind. Correct formulas first, forget about the balancing. Once you have all the correct formulas down, then you should balance. And it's a very common mistake that people make to try to do both at once, especially, for example, if you're given something on the left-hand side of the arrow and you got to kind of predict what's on the right-hand side of the arrow. People try to balance it and write the formulas at the same time, but you don't want to do that. Always formulas first and then balance. Also remember that when you're writing formulas, things like hydrogen, nitrogen, oxygen, chlorine, bromine, those are diatomic. So you need like H2, O2, N2. You don't want to just put H or O. So those guys come as twos, and you got to make sure that you put those in the formulas that way as well. This is what is represented as an unbalanced equation, and this is basically molecular hydrogen reacts with molecular oxygen to yield water. This is what these guys are sometimes referred to as molecular hydrogen, molecular oxygen. It's just like the element by themselves. To yield is what the arrow represents, and water, which is on this side of it as well. This equation is unbalanced, and it is unbalanced because when we look at it, we don't have the same numbers of each element. So if you made a little table in terms of hydrogen and oxygen, on the left-hand side, we have 2 hydrogens. Right-hand side, we have 2. Left-hand side, we have 2 oxygens. Right-hand side, we have only 1 oxygen. So it is not balanced. Remember, in a chemical reaction, the only thing that happens is we break bonds and we make new bonds, which means we don't touch anything in the nucleus like protons. And because we don't touch the nucleus or protons, we have the same number of elements on each side of the arrow. So if you started with 4 carbons, you should end with 4 carbons. You should not create or lose any atoms along the way. So the way that we fix this is we do have to put coefficients, and that is how we balance an equation. We only change the numbers that come in front, which is the coefficients. We don't change the smaller subscripts, because if I change that, what happens? No longer water, right? If I take the 2 out of there, right? So it's now something else. So we never change that. We never put big numbers in between elements or anything like that. So again, to balance it, we simply put numbers in front like a 2. When I put that 2 in front, it goes to both of the things behind it. That would mean that I have 4 hydrogens, and 2 times 1 is 2 oxygens. This is also very common when you go to balance equation. You fix one thing but screw up something else. So now that I fix the oxygens, the hydrogens are messed up, but I can easily fix that by also putting a 2 in front of the hydrogen on the left. That will give me 4 hydrogens and still 2 oxygens. And now I have a balance equation again by just changing the coefficients, and that is the only thing that you should change. Any questions on that there? So again, we could balance it by putting the appropriate coefficients, and we have a balanced equation. When we look at an equation, there's a few parts to it. On the left-hand side, those are reactants. So these guys over here are reactants, which is our starting material. And on the right-hand side of the arrow, those are our products, which is obviously what is produced as a result of this reaction. Now, we also will sometimes see other things written in the equation. Some of the other things that we see written in the equation are the actual states of everybody. So S for solid, L for liquid, G for gas, and I think it's on the next slide, but AQ is aqueous. And that does mean a water environment. So a lot of times you will see these little sort of states written next to the formulas in a reaction to indicate those things. We also will sometimes use chemical reactions to indicate physical changes. So if we look at this, that is liquid water going to ice. That is freezing water. That is a physical change, but we sometimes will use an equation to represent that. Same thing here. This is liquid water going to steam, which is evaporating water, which is a physical change, and we sometimes use it. We sometimes use an equation to show that we're dissolving something like in water. So sometimes water might be up there. And we'll sometimes use an equation to show that we're going to take this solid basically and sort of dissolve it in water in this particular case. Questions on that there? That's what we just did there. Right. By the way, there is a difference between aqueous and liquid. They both are in the liquid state, but a liquid is a pure substance like if you just had water by itself. If you took a pure substance like water and you mixed it with sodium chloride, like on this slide, it will dissolve and make a sodium chloride solution, which is basically this. And that is the difference between aqueous and liquid. Liquid is basically just one thing by itself, nothing mixed in it. And really, aqueous is a solution which is actually a homogeneous mixture. Everything looks the same throughout, everything mixes and is good. And we'll talk more about that, where waters are solvent and our sodium chlorides are solute that is being dissolved in there. All right, so let's talk about the steps to balancing equations. This is one sort of approach. You can write the correct formulas on the left and right-hand side of the equation. That definitely is something if you're given it in words. You want to, again, make sure you have the correct formulas down. You then want to start balancing the most complicated ones first with appropriate coefficients until you have the same number on each side of each element. The two things that you need to make sure of when it's all said and done is that all your coefficients, when you have a properly balanced equation, are whole numbers. So they all has to be whole numbers when you're done balancing the equation. And they has to be the simplest set of whole numbers. So what does that mean? Let's just say you had an equation like this, 2a plus 4b goes to 6c. And we'll just say that this is balanced, this equation. But with all these coefficients, I could divide them all by 2 and reduce them down to still whole numbers of like a plus 2b goes to 3c. That would be the properly balanced equation. And that sometimes happens because you can see larger numbers, some people, and it can definitely still be balanced with bigger numbers. But if you see that you could look at all your coefficients and you could reduce them down by a common number and still have whole numbers, you should do that to have a properly balanced equation. So that does happen. All right, so here's another approach. I'm just going to talk about my approach, I suppose. Maybe a better way. All right, let's take a look at one here. Let's say we have this equation and we wanted to balance it. So what I would personally recommend is actually to make a table. And sometimes by making a table, it just allows you to maybe figure out where you want to start with. So there's the reactant side, which is the left-hand side. There's the product side, and basically just list the elements: nitrogen, oxygen, hydrogen. So if I look on the left-hand side, I have 1 nitrogen. On the right-hand side, I have 2. Left-hand side, I have 1 oxygen. Right-hand side, I have 1. Left-hand side, 2 hydrogens, and right-hand side, 2 hydrogens. So by making this table, it's very clear to me that nitrogen is the only thing unbalanced, and that is probably where I should start. Remember that when we go to balance this, we're just using coefficients, which means I'm going to put a 2 here on the left-hand side. That 2 again goes for everybody behind it. So that means I have 2 nitrogens. I also will have 2 oxygens and still 2 hydrogens. Once again, that's very common that you add a number and it messes somebody else up. But again, looking at my table, I now know that probably oxygen is a good place to go to next, since that's the only thing that is not balanced. I could fix that once again by putting a 2 in front of the water, which again goes to both of these guys here behind it. That gives me 2 nitrogens, 2 oxygens, and 2 times 2 is 4 hydrogens. We're getting really close at this point. That means that all I have to do now is come back to the left-hand side, fix up my hydrogen by also, in this case, putting a 2. Seems to be a winning number here. That gives me 2 nitrogens, 2 oxygens, and 4 hydrogens. And now I will have a balanced equation. Any questions on that there? All right, why don't you try one then? Why don't you try this one? Balance this one up, see what you come up with. Okay, let's take a look. So again, I'm going to make a little table here. I got carbon, hydrogen, oxygen. Left-hand side got 3 carbons. Right-hand side got 1. Left-hand side I got 8 oxygens or hydrogens and 2 on the right. Oxygen, I got 2 on the left. On the right-hand side, I do have 2 oxygens there, and we do not want to forget the other oxygen that's over there, so that's a grand total of 3 in this case. Again, 1 and 1 and 2 in the other guy. Here, again, not much balance. Here, personally, I would go with what seems the easiest to balance. And to me, carbon's just in one thing on each side, and I could just easily balance that. So that is where I'm going to start. I could put a 3 in front of it. Again, that 3 goes to both of the things behind it, which means I have 3 carbons. I now have still 2 hydrogens. Now, in terms of oxygen, 3 times 2 is 6 in the first guy, and I still have 1 in the second. And that gives me a grand total of 7 oxygens I got going on at this point. Again, at this point, I have now fixed the carbon, so I have my choice between hydrogen and oxygen. My opinion is here, I am going to go with hydrogen first. The reason for that is when I look at oxygen, it is over here by itself, but it's in a couple of things over here. Might as well save that guy for the end, since it's in multiple things. So here again, the hydrogen is going to be probably easier to balance because it's just in one thing on each side. And we can balance the hydrogen by putting a 4 in front of it. And that's going to again go to both of these guys here. And that will give me 3 carbons. 4 times 2 is 8 hydrogens. And now in terms of oxygen, I still have 6 on the first one, but now the second one will be 4. And now I have 10 oxygens left. And this is why I saved oxygen for the end, because now I could easily fix that by going to my oxygen on the left and putting a 5, yeah? And we will have 3 carbons, 8 hydrogens, and 10 oxygens. Questions on that there? All right, one last one here. Balance that guy up. Okay, let's take a look here since we're getting to the end. We got 2 borons on the left. Here we have 1. Oxygen's on the left. We have 3 here plus 1 more there, which is 4. Oxygen's on the right. This is a polyatomic ion. We do need to multiply that guy into both of them that's in the parentheses. So that would be 3 for the oxygen there. Hydrogen on the left, 2. Same thing. We're going to multiply in, and we have 3. Not a lot to work with here, so might as well again start with the boron, which is the easiest to fix. We will put a 2 in front of it. That's going to give me a 2. This 2 goes to the boron. It also goes to everybody else behind it as well. That means when we look at oxygen, we have 3 times 1, which is 3, times 2, which is 6, and 3 times 1 for the hydrogen times 2 in the front is 6. So you do have to multiply in and then multiply out by the coefficient that's in front there. Once again, we fixed the boron, but we have hydrogen and oxygen that is next. Once again here, I'm going to choose to save oxygen for the end because it's in multiple things. So I'm going to go with the hydrogen next, which is much easier to balance since it's only in one thing. Looking at the hydrogen to balance it on the left there, I would need a 3, which goes again to everybody behind it. That's going to give me 2 borons. In terms of my oxygen, I have 3 here and another 3 right there, which gives me 6. And 3 times 2 gives me 6. So in this case, by saving the oxygen for the end and just balancing the hydrogens, it fixed both, which sometimes happens. You put a coefficient and it fixes everybody else that you need. Any questions on that there? All right, we'll lay it up there